Welcome to the last video in our lesson on cardiac muscle. In this video we're going to talk about the myofilaments and how they respond to calcium to contract and how that contraction takes place. And then we'll talk about the process of relaxation just a little bit. So first of all, this is a bundle of myosin molecules. So you guys know your thick filament made up of myosin. This is a thick filament. It's a bunch of myosin molecules that are sort of arranged in parallel with these heads, these cross bridges that stick out like golf clubs out of a bag, okay? Each of these myosin molecules, particularly the myosin heads, has an actin binding site and a myosin ATPase binding site. And we will talk about how those interact to cause contraction in a moment. And the myosin heads stick out and form cross bridges with the actin when the muscle is contracting. So we can call them myosin heads or cross bridges. Okay. Your actin molecules are basically these little balls. And what happens is they self-assemble to form this actin helix, this filament here. So you can see these are sort of assembled here in a helix. This is your actin molecule here. This is a binding site for myosin. So this is where your myosin head will connect to the actin when you contract. And then also as part of the thin filament, we have tropomyosin, which wraps around the actin, and we have troponin, which sits in between the tropomyosin and the actin. And you will note that, see the three little circles here, there are three subunits of troponin. We have troponin T, which connects tropomyosin, which binds to tropomyosin. We have troponin I, which binds to actin, and we have troponin C, which sits in between, and it's called troponin C because it binds calcium, okay? Which is very important, which we'll talk about in a second. So here's our thin filament. We have our actin helix here. We have our tropomyosin wrapped around our actin helix, and you'll notice that when the cell is at rest, not contracting, the tropomyosin sits right over these myosin binding sites on actin, so that myosin can't bind to the actin and can't cause a contraction, okay? And then we have our troponin sitting in between the tropomyosin and the actin, okay? All right, so this is how our filaments are arranged. This is a cross section through the A band. So the A band has overlap of the actin, the thin filaments here, and the myosin, the thick filaments here. The thin and thick filaments. So you have thin filaments which are blue, you have thick filaments which are red, and you can see they are arranged such that the actin surrounds the myosin, and the myosin, each actin, the thin filaments surround the thick filaments, and each thin filament is surrounded by thick filament as well. So you can see how these are arranged in such a way that these myosin heads can reach across and bind to the actin and cause contraction, okay? All right, so here's how it all works, sort of in general. So you have your thin filament with the actin here, your tropomyosin wrapped around, covering up the myosin crossbridge sites, okay? And you'll notice that here's my myosin molecule, and it's not bound to actin. And it's not bound to actin because these are the sites that it has to bind to in order to do that. So we're not getting any contraction here. Contraction takes place when myosin binds to actin, okay? So what happens is your cell, through this process of excitation, contraction, coupling, which I described in the last video, you get an increase in calcium in the cytosol. And when that happens, calcium binds to troponin C, and you get a shift such that now this tropomyosin, which is connected to the troponin C through troponin T, moves. And it moves away from the myosin binding site on actin, okay? And when it does that, it allows myosin to bind to the actin, and when it binds to the actin, you can get contraction, okay? So calcium, increased calcium in the cytosol causes the troponin, the tropomyosin to be moved away from the myosin binding sites on actin, such that the two can interact, and now you can get contraction. Okay. So, one thing you'll notice, troponin I is in here. Again, it's one of these subunits of troponin. And it's actually called I because when it's phosphorylated by protein kinase A, which is what happens when you have beta-adrenergic stimulation, you have an increase in sympathetic activity, and norepinephrine binds to beta receptors. You get activation of protein kinase A, it phosphorylates troponin I, and it decreases the affinity of troponin C for calcium, which means it makes it so that may not make a whole lot of sense to you guys. You went through my first lesson, the introduction to the cardiovascular system, and you know that usually when you have an increase in sympathetic activity, you have an increase in force of contraction of cardiac muscle. So that increased sympathetic activity makes the muscle contract harder. The increased force of contraction and the cardiac muscle increases stroke volume, and you increase cardiac output that way. Okay? So it probably makes zero sense to you guys that phosphorylation of troponin I through beta-adrenergic stimulation, that is an increase in sympathetic activity, would actually cause a decrease in binding of calcium to troponin C, not an increase. Well, it turns out that you get so much more calcium increase in the cytosol when you have an increase in sympathetic activity, that despite the decrease in affinity of troponin C for calcium, you still get a big increase in force of contraction. In other words, yes, there is a decrease in the affinity of troponin C for calcium, but the increase in calcium in the cytosol is so big that it doesn't matter, and it overwhelms this decrease, and you still get an increase in force of contraction. So you might ask yourself, why do I have a decrease in the affinity of troponin C for calcium then? The reason is because after the increase in calcium is over, and as calcium is going down during relaxation, this increased phosphorylation causes troponin C to release calcium quicker. And when it releases calcium and calcium unbinds from troponin C, that allows relaxation to take place faster. So when you have a high heart rate, your heart doesn't just have to contract harder and faster, it also has to relax quicker because you have to get ready for the next beat, and you have to do that faster in a heart with a high heart rate. So this phosphorylation of troponin I contributes to that and allows you to do that. So you get a faster relaxation and you're ready for the next beat a lot sooner, okay? And that's why that takes place. Okay. So what does binding of myosin and actin do? Well, here we have sort of a schematic of what happens. So as I said, calcium goes up, tropomyosin moved away from the myosin binding sites on actin. Myosin can now bind to actin and form a cross bridge. And what you get after that is what's called a power stroke. So you can think of this myosin as being cocked and ready to go, and all it's really waiting to happen is for calcium to go up. And once calcium goes up and that binding site is exposed, bam, myosin binds, and as it binds, there is a conformational change in the myosin head such that you go from cocked to bent. And the myosin bends, and as it bends, it drags this actin this way, okay? And so what you get are these two myofilaments, the thick filament and the thin filament, moving in opposite ways parallel to each other, okay? So this power stroke actually causes contraction through the sliding filament mechanism. That is, you have actin molecules, You have thin filaments moving this way as that power stroke takes place, and you have myosin moving, myosin heads, well, they don't actually move, they're sort of anchored in the center of the cell. But you can see these two myofilaments, the thin filament and the thick filament, they sort of move over one another. And the thin filament is moved toward the center of the cell, and so contraction takes place through this sliding myofilament mechanism, okay? So we have our thin filament and our thick filament. As this power stroke takes place, the actin moves this way, and you can see it actually moves this way, let's say on this end of the cell, and as that happens, the cell contracts, okay? And your Z line is actually dragged toward the center of the sarcomere, okay? We then get detachment, and the myosin detaches from the actin, and it is ready to bind again, assuming that the calcium remains high, and form another cross bridge, and then you get your power stroke, and it bends, and then you get detachment again, okay? So that's basically how cardiac muscle contraction works. So in order for this to happen, this explains the actin binding site on your myosin head. What about your ATP binding site? Well, you have this myosin ATPase site because you need ATP for contraction to happen. So let's see how that integrates into all of this. So let's start our cycle of contraction at step number 1 here. And at step number 1, we're in a state where ATP has actually been split. And so we have ADP and phosphate bound to this myosin head. And the myosin head is actually in a cocked state, okay, ready to bend, but it's not bending. The reason it's not bending is because when the cell is at rest, there's no calcium. And if there's no calcium, then the tropomyosin is covering the actin, the myosin binding sites on actin, and the myosin head can't interact with the actin, okay? So with no calcium, this is where you sit. Your myosin head is cocked and ready to go, but it can't go because it can't bind to the actin. The tropomyosin's in the way. So we call this the resting state of the muscle. What it really is, it's the state of the muscle that it's the state that the muscle is in during diastole, when the ventricle is filling, and as the ventricle fills and it adds that stress onto the walls gradually, the muscle gradually expands. Well, it expands because there's relaxation taking place. There are no cross bridges formed, so it's very easy for that blood to sort of push those walls out and allow the muscle to lengthen and the walls to expand and accommodate the blood. Okay, so you can think of this as being a state where you're allowing the actin to sort of be to move this way, and assuming that you're going to contract and move it this way, the actin, as the blood fills the ventricle, the muscle is lengthening, and you're dragging your actin sort of that way, and you're able to do that because there's no active cross bridge in between the actin and the myosin. It just naturally can slide as the blood gradually sort of causes that myofilament to expand. Okay, so this is the situation during diastole. Your muscle is relaxed, it's not contracting, there are no myosin cross bridges, and as the ventricle fills, the myofibrils lengthen and the chamber of the ventricle expands. Okay? All right. On the other hand, if our action potential comes in, and we get calcium coming across the sarcolemma, we get calcium released from the SR, the calcium increases in the cytosol. Now we move our tropomyosin molecule out of the way because calcium is binding to troponin C, and we get a connection, a binding of the myosin to the actin. And you can see that here. You get binding with the cross bridge, and you get a connection here, okay? Once that is established, you get what's called the power stroke. So you can see we're cocked here, and here we're bending, and as we bend, we move our actin molecules this way, right? So contraction is taking place because if my Z line's out here, it's moving this way along with the actin, and it's moving toward the center of the sarcomere. And so this is our power stroke, where the myosin head bends, right? And as that happens, ADP and phosphate are released from the myosin head, okay? And the myosin ATPase site is actually now open and ready to bind another ATP molecule, okay? And that's exactly, so you might ask yourself, what happens if there's no ATP left, like if you're dead? Well, what happens is with no ATP, your myosin power stroke takes place, you bend, and then you just sit there connected to the actin. And so this is called formation of a Riger complex, okay? And basically, it means that your muscle can't relax, and it just sits contracted, and that's all it is, okay? So in skeletal muscle, if you were to feel these rigid muscles in a person who's passed away, you would call that rigor mortis, okay? However, we would hope in our alive heart that would not take place. So let's assume that ATP is available. And assuming that ATP is available, what's going to happen is it's kind of come in and it's going to bind to this myosin ATPase site. And that is going to cause the myosin head, the bent head, to detach from the actin. Okay? And this is how detachment takes place. Okay? And then what happens is ATP is hydrolyzed, you get the formation of ATP and phosphate. As that happens, your bent head now becomes cocked again. Okay? And you can see it's cocked, unbent, and ready to contract again. And if the calcium remains high, that'll be what will happen. You'll just immediately bind to the actin again, and then your power stroke will take place, and you'll drag the actin further that way. If calcium is falling, so that there's very little calcium, then you just sit in this state, and the myosin can't bend, and so this is the resting state of the muscle unit. All right? So that's how it works. And we start all over again. There it is. Okay? Okay. So the process of relaxation takes place because calcium falls. Okay? And once calcium falls and troponin C is not bound to calcium, the tropomyosin moves back over the myosin binding site on actin, and then you can't get that interaction anymore. And you don't get any more contraction. So, what happens here is the L-type calcium channels close when this action potential is over and the membrane is no longer depolarized. Okay? And because they close, there's no more calcium-induced calcium release taking place. These ryanodine receptors close as well, the SR calcium release channels. And so there's no more SR calcium release, there's no more calcium coming across the membrane, and therefore calcium in the cytosol falls. And the reason it falls is because of two molecules. You have your SR calcium pump, which brings calcium from the cytosol back into the SR. It pumps calcium from low concentration to high concentration by hydrolyzing ATP. So this is a primary active transport. Okay? The calcium is reaccumulated in the SR, and as that happens, the calcium falls in the cytosol. The other thing that happens is primarily your sodium calcium exchanger carries calcium from the cytosol into the extracellular space. So as you guys know, we have high sodium on the outside of the cell, low sodium on the inside of the cell. Sodium wants to go from high concentration to low concentration. That concentration gradient is established by your sodium-potassium ATPase, right? And so as sodium goes down its gradient from high concentration to low concentration, that can't take place through the sodium-calcium exchanger unless this protein transports calcium in the other direction. You get calcium transported from low concentration to high concentration as this transport of sodium down its gradient takes place. So this is secondary active transport. The sodium-potassium ATPase sets up the sodium gradient. The sodium gradient is used to transport calcium uphill to the extracellular space. So both of these things contribute to the decline in calcium that you see that allows relaxation to take place. The other thing I want to point to, as is noted on the text on the slide, we have this molecule called phospholamban. Phospholamban is ordinarily bound to the SR calcium pump, and when it's bound to the SR calcium pump, it actually inhibits it, okay, and slows it down. This is a protein that exists all the time in the SR, and its natural state is to bind the pump. When you stimulate this muscle, let's say through increased sympathetic tone, or by giving a beta-adrenergic agonist, okay, what happens is this phospholamban becomes phosphorylated by pKa. And when it's phosphorylated, it can't bind to the SR calcium pump anymore, and the inhibition that is normally caused by phospholamban is relieved. And when that inhibition is relieved, it accelerates SR calcium uptake. The pump is accelerated, and you move more calcium from the cytosol into the SR. So this accelerates the process of relaxation along with the phosphorylation of troponin I, which I talked about on an earlier slide. Okay, so at high heart rates, you want to get that calcium down as fast as you can, and you want the myofilaments to release that calcium as fast as you can. And so these two changes with sympathetic stimulation are meant to allow that to happen. All right, let's talk a little bit, now that we've talked about how the muscle contracts, about the length-tension relationship. So this is the length. We're going to have to talk about skeletal muscle before I can talk about cardiac muscle. So this is the length-tension relationship for skeletal muscle. Okay, and the first thing you'll note is that in skeletal muscle, in resting muscle, you actually sit here on the length-tension relationship. So this is really the peak efficiency for the muscle when it's at this length. When it's at lower lengths, you don't contract with as much force. And when it's at higher lengths, you don't contract with as much force, okay? So if your skeletal muscle is sitting here and you stretch it to a longer than normal length and then stimulate it to contract, it will contract with less force. If you take it and you make it a shorter than normal length and you stimulate it to contract, then it will contract with less force as well, okay? So this is skeletal muscle. This is where it optimally sits at rest, okay? If you stretch that muscle to a greater length and then stimulate it, you get less force. The reason is because as you stretch the muscle, you have less overlap between actin and myosin here. You can actually count the actin molecules here, 1, 2, 3. You can count them here, there are only 2 that are overlapping. Okay, so as you stretch, you get less overlap. If you have less overlap, you have less cross bridges form. If you have less cross bridges form, if you have less actin and myosin binding taking place, then you get less force of contraction. Okay, and if you go down in length, you get less force as well. In this case, you can kind of see that there's like overlap of the actin molecules now, where you've got so much contraction that the actin molecules are actually sliding over one another. And so the molecules that are in this area can't get to the myosin because there's an actin in between. So we have an actin here and actin here. This one can't get to the myosin. And so there is, again, less overlap. And so you get less force of contraction at lower muscle lengths. Okay. So that's skeletal muscle. So you might say, why are you doing this, Dr. Shannon? We don't care about skeletal muscle. Well, this is what happens with cardiac muscle. And the first thing you'll notice is that cardiac muscle operates on the ascending limb of this curve, on this part. It does not operate here where skeletal muscle operates. Okay? The reason is because cardiac muscle can't even be stretched into the descending part of this curve. If you try to stretch cardiac muscle too far into the descending part of this curve, it actually breaks. The fibrous tissue in the cardiac muscle, the series elements, don't allow you to stretch the muscle that far. And so in order to do it, you have to actually break those elements, and you have to damage the tissue. So cardiac muscle never makes it very far into this part of the curve, if at all. And so what that means, cardiac muscle sits here. It doesn't sit at the peak. And if you increase the length of cardiac muscle, you always increase the force of contraction. Okay, so this is the length-tension relationship for cardiac muscle. You can ignore this part altogether, so that it makes it different than skeletal muscle. Okay. So this is sort of the length-tension relationship for cardiac muscle here. And you can see we have almost none of the descending part of the curve here. So as you increase the initial muscle length, if you increase the length and then stimulate that muscle to contract, you get a given force, and if you increase the length, you get more force. Okay? So this is length-dependent increase in contraction. Okay? We call this the Frank-Starling mechanism. Dating back way into the early part of the 20th century when they discovered that this actually happened. Okay? So that is one way to increase force development in cardiac muscle. You increase the length of the muscle. This is important, by the way. If you increase the filling of the ventricle, it stretches these muscle fibers more. And if you stretch the muscle fibers more, they contract with more force and you get a higher stroke volume. So the more filling you get in the heart, the more you stretch the ventricular walls, the more you stretch the ventricular walls, the more force of contraction you get, and the higher the stroke volume. Okay? And you would always want that to take place in a normal heart. If you're getting more volume during relaxation, you want to be able to eject that volume during contraction. And this mechanism, in part, allows you to do that. Okay? The other thing that increases force of contraction that I want to address in this video is contractility. Okay? So an increase in contractility means that you have an increase in force of contraction at the same muscle length. Okay? So let's say I have a strip of muscle and I stretch it to this length, and this is the force of contraction in my control muscle. Okay? And now I look at that muscle after I've added a beta-adrenergic agonist, or after I've stimulated it with a sympathetic sympathetic nervous system. And now it's stretched to the same length, meaning if you're in the context of the heart, you're filled to the same volume. And now if I stimulate that cell after adrenergic stimulation, look what happens. I've increased the contractility, and that means I get more force of contraction at the same length compared to my control without the sympathetic stimulation. Which means that if I've filled the heart to the same volume, and I've stretched the muscle fibers to the same extent, if I've stimulated that heart with a sympathetic nervous system, I will get more force of contraction and therefore more stroke volume at the same muscle length, that is the same filling volume. Okay? So increasing contractility increases my stroke volume. But notice this is not the same thing as increasing the length of the fiber. It's not the same thing as increasing the filling of the ventricle, which will increase your force of contraction only because you've increased the muscle length. This is muscle length independent. It says more about the state of the muscle itself. It means that you've changed the muscle in such a way that you get more force of contraction at the same length. Okay? And if you decrease contractility, you get less force of contraction at the same muscle length. So this would be an indication of disease. Okay? So typically, particularly if we're talking about the pharmacology of the system, you're talking about an increase in calcium in the cytosol causing an increase in the force of contraction that would be characterized as an increase in contractility. So if you get an increase in certain hormones, or if you get an increase in sympathetic tone, or a decrease in parasympathetic tone, if you're talking about atrial muscle, then that will cause an increase in force of contraction at the same muscle length. A length-independent increase in force of contraction. And again, this is usually how inotropic drugs work. They cause more calcium to be released, and that causes more myosin to be able to interact with calcium because you're binding to more troponin C, and that increases the force of contraction. Okay, and therefore stroke volume. Other factors can be characterized as an increase or decrease in contractility, or an increasing or decreasing inotropic state, which is another name for it. Okay. These include the number of functional myocytes. So if you have a heart and you have a blockage of a coronary artery, the myocytes that are supplied by that coronary, not real functional. And so we would characterize the result of that blockage and the result of the fact that you've got less oxygen in that area as a decrease in the inotropic state of the heart, okay? Because you've got fewer functional myocytes in the walls of the ventricle, which are cutting off oxygen to a certain number of those myocytes, okay? So students frequently ask me, how do you differentiate inotropic state or contractility from other factors that affect the contraction of the heart? Well, if it isn't a change in muscle length, meaning it isn't an increase or a decrease in filling, and if it isn't a change in afterload, which we'll talk about in a later lesson, then it's a change in inotropic state, and that's how you tell the difference. So most students know what increased filling means, and so they go, well, it's not an increase in filling, so it must be a change in inotropic state. We'll talk about that in a later lesson. But for now, do know that a change in contractility is a change in force of contraction when the muscle is at the same length, okay? And it's important to be able to differentiate that from changes in length and changes in force and contraction due to changes in length, because increases and decreases in force of contraction with changes in filling or changes in muscle length, that's normal. Increases that are independent of muscle length, that's not normal. That means you either did something to make it contract more, or a disease did something to make it contract less. So changes in contractility usually means that there's an indication that there's a disease present, or there's a drug present, or you've done something physiologically to make that muscle contract more or less. Okay? All right. That's all I've got for this video. Thank you for your attention, and I will see you guys in the rooms.